Okay, so I gave you a matrix. Example. Now A equals equals what? A equals the 1, 2, 4, 3, 0, 5, -2, -3, 1. So calculate the determinant of A inverse. Try this one for me, okay? I give you guys 1 or 2 minutes. Okay, did you get it?
This one number -47.
-47, no. Should be a 1/5. Determinant of A inverse. That is 305, -2, -31. What is your determinant of A?
-47.
I don't think so.
Yeah, I got a negative number too.
-2
Like negative number.
or negative?
I got it too.
Okay, later I'm gonna do it on board. Okay. Now let me do it on board. So determinant of this guy. So positive, negative, positive, negative. So I will definitely want to try the second column. This guy gonna give you what? So the 2 is times negative, right? Cross out. With 3, 5, -2, 1. And the second one is 0, and the 0 times the positive, cross out. That is 1, 4, -1, -2, 1. -3 times -1. Okay. 1, 4, 3, 5. Okay, -1. And 0 and 2. 2 is -1. 3, 5, -2, 1. 1, 3, 4, 5. Okay, so -2. 3 times 1 minus -2 times 5. The plus 3. 1 times 5, 3 times 4. Okay, -2. 3, -2, 10. 3, 5 minus -12. And this guy is 13, -26. And this guy is 5. Oh, you got a negative. -10, -21. I made a mistake maybe. So it's negative 47. Did you get the same answer?
Yeah.
Oh, okay, that's wrong. So I make a mistake. And negative 47. Good job, guys. I made a mistake. Okay, so the determinant of this guy gonna be 1 over a negative 1 over 47. That's it. Okay. So today I'm gonna teach you guys the properties, the equivalent conditions for a non-singular matrix. Now let's take a look. Equivalent conditions for a non-singular matrix. If A is an n by n matrix, then the statement below are equivalent. Equivalent the first one, A is invertible. Okay. Second one is A has an unique solution for every n times 1 column matrix B. 3. AX has only the trivial solution. Fine. 4. AX A is determined A doesn't equal 0. Okay, so so let's take a look at the equivalent conditions. So if A is singular or is invertible, means singular. Okay. If A is invertible, that means what? That means determinant of A doesn't equal to 0. That's what we learned from the last class, right? If the determinant doesn't equal 0, that means this matrix can be invertible. But the determinant couldn't tell you what is exactly A inverse. It only can tell you whether this matrix is invertible or not, okay? But couldn't tell you what is exactly the inverse it is, okay? So another thing is we always try to use our conditions or the properties, apply the properties to the equation system. That's our purpose, okay? So if the determinant doesn't equal 0, that means this guy has a unique solution. Why is that? Take a look. This guy has a unique solution. If this guy doesn't equal 0, that means A is invertible. So we can times A inverse for both sides. Okay, we times A inverse for both sides. That's equivalent. Since this guy is I identity X, identity matrix. Identity matrix times X always equals itself. Since the inverse of A is existed. So that means A inverse times B gonna be the solution of X. Okay, so we have a unique solution. Otherwise, if the determinant of A equals 0, you couldn't do the inverse of A, right? So that's the reason we can say if that guy doesn't equal 0, that means we have a unique solution like that. Okay, unique solution like that. Very similar for this guy. This guy has the trivial solution. That means what? That means X equals 0. All right, X equals 0. And why is that? We can prove it. We're gonna follow the same strategy here, just times the inverse for both sides. Times the inverse. And we see this is the identity matrix. I times is X, and this guy times 0 equals 0 matrix. So you can prove it. That guy has the trivial solution under the condition determinant of A doesn't equal 0 or A is invertible. Okay, so that's for we call our equivalence. If this equation has the trivial solution, that means X equals 0. Okay, all the solution equals 0. That means A is invertible and the determinant of A doesn't equal 0. If this guy has a unique solution, that means A is invertible or this guy doesn't equal 0. So all these 4 conditions are equivalent. Okay, if you know one condition, you should know the other 3. Now, let's take a look. which of the systems has a unique solution. Okay, so for example, the first province. So if I give you such 3x3 linear equation system, of course, you can write down the augmented or not augmented coefficient matrix. Oh, sorry, setting. X1 is 0 to -1, 3. Okay, you can write down it's a matrix form. Okay, I think you guys already get very familiar with such transformation, right? You did a lot of homework, so that's the typical way how to write this matrix way. So that's the coefficient matrix. That is x, x1, x2, x3, and that is b, 1, 4, -4. Okay, b is a constant. Okay, so for this system, it's just like ax equals b, right? Like this guy. We want to check whether the system has a unique solution. That means what? That means what? Like I said before, if we want to check this guy has a unique solution, that means we just need to find the other condition satisfied. So the easiest way is what? Use the determinants. Okay, determinant. If determinant doesn't equal 0, that means that guy has a unique solution, right? Okay, so what is A? Is this guy. We just need to calculate the determinant of this guy, whether this guy equals 0 or not. If equals 0, that the system doesn't have unique solution. Or if equals 0, doesn't have. If doesn't equal 0, that means has a unique solution. Right? Now try it. Calculate the determinant of A. Okay, try it. How about the determinant of A? What's the determinant of A? So determinant of this A should be equals 0. So that means the system doesn't has unique solution. Okay, now I want you guys to try this one for me. The same first two. And we have a slightly different for the last one. Now try this one for me. Check whether the system has a unique solution or not. Okay, now let me write down the answer. Write down the answer. Okay. So for this guy, we can calculate the determinant 0, 2, -1, 3, -2, 1, 3, 2, 1. And the determinant for this guy is -12 doesn't equal 0. And the only difference for this is the last term. It's 1. Here's a negative. Okay. So, but I gave you a totally different number. That is -12. So this system has unique solution. Okay, unique solution. Okay, now let's continue. Theorem. (3.9) if A is a square matrix, then determinant of A equals determinant A transpose. Okay, that's very important property for the determinant or for the A transpose. Okay, A transpose. the determinant of A equals determinant of A transpose. Transpose. Okay. Now, I want you guys show that determinant of A equals A transpose. What are you gonna do? Yes. Have A is what? A is 3, 1, -2, 2, 0, 0, -4, -1. Fine. Okay. Now prove that. So how to prove? You need calculate the determinant of A. Also, you need to calculate the A transpose, then do the determinant. If these two equals to each other, that means these two are equal, right? So just prove it. Did you guys take the proof class before? Yeah, great. So you know how to prove. Okay, I'm gonna write down the answer on board. So for this guy, the first thing you can calculate the left-hand side. Of course, you can do the expansion according the second law, right? Second law has the most zeros. I can do it. Positive, negative times negative. So we have 1, -2, 1, 5. Right? Positive, negative, positive. So 0, you don't need to care because 0 times everything gonna equal 0. -2, 5, and this guy gonna give you -6. And for the A transpose, you know how to calculate the A transpose. A transpose is gonna be what? Transpose, the column becomes row, right? The column becomes row. That yes, that should be right. 3, 2, 4, 1, 0, -1, -2, 0, 5, -2, 0, 5. Okay. Oh, yeah, you're right. So this guy, you can do the expansion according to your second column, right? Second column. So negative, positive, negative. So the same thing, you're gonna get 2 times negative 1. You still get negative 2, 5. Okay, cross product 2, 5. You're gonna get negative 6. So we just prove it. We prove this guy equals. Okay, we finish it. We finish it. Now today I'm gonna teach you guys something different. Some of you guys already learned it from your calculus class. That is vectors. Vectors. Okay. So let's take a look the definition of vectors. I'm gonna do it very quickly because some of you already take the calculus, and the calculus already address the vectors. Did you take the calculus?
Yeah.
Yeah, so you already learned the vectors, right? So I'm gonna go through these vectors a little bit quick. Okay, let's take a look at the vectors. 4.1 vectors. In n-dimensional space. A vector is created with length and also direction. And by definition, a vector can be drawn as a picture like that. You have initial point, x1 is 0, 0, or starts with origin, initial point, and x1, y1, that is a terminal point. Okay, so we have 2 points, and we also has the initial point. Well, I mean, we have also has the direction. Okay, direction and the length. This is length. This is direction. The arrow is the direction. Okay, and then we can say x1, y1, the component. Component of vector x. Okay, so that's the definition for the vector x. It should supposed to have the initial point. Initial point always be in the origin, and the terminal point can be at any coordinates. Okay, so let's take a look the property. Okay, the property. The first property going to be here. And equal if u1 equals v1 and u2 equals v2. Okay, that's the first property. If these two vectors equals each other, that means u1 equals u2 u1 equals v1, u2 equals v2. Okay, so that's the property. That's the property. And another one, vector addition. If u vector plus v vector, we just let these two add together. The first component add the first component, the second component add the second component. Okay, second component. And we also have the vector subtraction. Subtraction. Okay. U subtract v. U subtract v gonna be u1, v1, v2. So the first component subtract the first component u2. Right. Of course, there can be a zero vector in two-dimensional space. The zero vector in two-dimensional space can be write down as this. Okay, so that's a zero vector space. Now let's take a look at some examples. Since you guys already know some basic idea about the vectors, I want you guys calculate the examples. Okay, some examples. Let's take a look. The first one, example one. U equals 1, 4. V equals 2, -2. Then calculate this guy for me. Try it. Okay, try it. Okay, now let me do it. Let me do it. Should be the first component plus the first component. Right, 3, 2. Now I want you guys to try this one for me. Okay, try this one for me. I can write down the, yeah, go ahead. Okay, let me try the onboard. So for this guy, we have what? We have u subtract v, 3 subtract -3, -2 subtract 2. We have 2, -4. Okay. C. Calculate the 1/2 for u equals 3, 4. Okay. Now, a scalar times a vector, how to calculate it? Try it as well. Okay. So now I'm gonna write down the answer for you guys. 3, 4, that guy equals 3/2. I mean, a scalar times a vector gonna be each element times the vector. Okay, times the scalar. Okay, that's it. That's it. Now let's take a look at the theorem or properties of the vector addition. Theorem 4.1. Property of vector addition. We have u plus v is a vector in the plane. Okay. 2 u plus v equals v plus u. 3 u plus v plus w equals u plus v plus w. 4 u plus 0 vector equals u. 5 u minus u equals 0 factor. 6 c times u vector is a vector in the plane. 7 c u plus v, that is c times u. 8 c plus d u plus du plus du. 9 c times du vector equals cd u vector. 10 1 times u equals itself. Okay, so that's the property of a vector, and it's a very regular vector distribution, association, anything. It's very similar to the real numbers. But be careful, what you're gonna do is as a vector, we always use this arrow on the top, right, to represent that is vector, okay? Now let's take a look the definition for the vector in n-dimensional space. Okay, previously I addressed the vector in two-dimensional space because we have two elements. Now I have n elements. Okay, so let's take a look. Definition of vector addition and scalar multiplication in Rn. Let U be U1, U2, blah, 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 blah. We have n elements. And the V, we have n elements. Be vectors in n-dimensional space. And let C be a real number. The sum of U and V is the vector UN plus BN. And the scalar multiple of U by C is the vector CU equals CU1, CU2. CUN. And the vector subtraction U minus V, U1 minus V1, U2 minus V2, U3 minus V3, UN minus VN. Okay. So that's the subtraction, scalar scalar multiplication. Okay, that's a scalar times vector, and the vector subtraction here is very similar to two-dimensional space. Just we add extra elements for the n-dimensional space. Now I'm gonna give you guys an example. Let you guys try it. So let's take a look at an example. U now try this one for me. V C try this one for me. Okay, let's take a look at this province. So the first province is addition. I think it's still very straightforward. Just let all the elements added together. That's it, fine. That's it. So we have -1 plus 2, 0 plus -1, 1 plus 5. And this is going to give you 1, -1, 6. V subtracted 2, -u. So V is 2, -1, 5, -1, 0, 1. Okay. And 2 times all the elements, because 2 is the scalar, right, times each element. And then subtraction 2 minus -2, -1 minus 0, 5 minus 2. And this is going to give you 4, -1, 3. And the last one, C. For the 1/3 U, 1/3 -1, 0, 1. Each 10 times 1/3 should be 0, 1/3. Okay, that's it. I'm gonna wrap it up. I'll see you. Thank you for coming. Have a nice day. Okay.